Hello, my name is Mona Lisa Das. Today I will be presenting the project for the course EL6562, that is Image Processing and Computer Vision. My project is on volume rendering using ray tracing and B-spline wavelets. We will begin with understanding what volume rendering is. Volume rendering is basically the projection of the volumetric datasets of a 3D scene into a 2D image. Now, volume rendering can be of two types: indirect volume rendering and direct volume rendering. In case of direct volume rendering, the geometric primitives do not have to be converted to some other intermediate domain before giving the volume units. That is why we have elected direct volume rendering for our project. As we can see, direct volume rendering makes use of something called voxels. What are voxels? Say you have a 3D dataset S of XYZ, where XYZ represents the coordinate position of the samples, then each sample is called a voxel, and in direct volume rendering, these voxels are obtained directly and they directly contribute to the final 2D projection. Now we will understand what ray tracing is. Ray tracing is basically the tracing back of the rays from a 3D scene to the eye or camera in a reverse direction. It makes use of what we can see as the illumination model. In the illumination model, the rays are cast directly from the center of projection of the camera, and then they pass through every image pixel in the imaginary plane. Then the ray is sampled throughout the volume, and by taking the intensity levels at every sampling point and calculating the weighted sum of the intensity values, the intensity of the entire imaginary plane can be deduced. However, interpolation in this case becomes extremely necessary since the sample points may not be integral lattice points of the data intensity level. Now we need to understand what B-splines are. B-splines are basically piecewise polynomials of degree m equal to n minus 1, where n is the order of the transfer function h and x in a variable x. This is a transfer function of a B-spline. Now, B-splines interpolation has different transfer function based on the type of variation regions. If there is no variation, then the transfer function is this. This is the transfer function of B-spline interpolation if the variation is linear. The transfer function for B-spline interpolation in case of cubic variation is this. Now we will study the implementation of this project on MATLAB 2009. For the purpose of this project, we have obtained the 3D dataset from the Brainwave Simulated Brain database provided by McGill University. The data volume of this dataset is 181 by 217 by 181. Now, the 3D dataset requires some index volume to be assigned to identify the type of interpolation which is required. The index volume can be generated along the coordinate axis by taking a slice along each of the three axes. The index volume is assigned values of 0, 1, or 3 based on the type of variations. The regions of constancy, there is no variation, are assigned values of 0, and it requires nearest neighbor interpolation. The regions of 1 are linearly varying regions, and it requires linear interpolation. The regions of 3 are the variation of cubic or higher degrees. As we can see, this is a representation of the original 3D dataset as simulated on MATLAB, and this is the representation of the simulated index volume. The regions in black are the index volume assigned with values of 0. The regions in gray and white are distributed between the index volume values of 1 or 3. Next, we will understand the interpolation which has been done for the purpose of this project. Primarily, we have done direct interpolation. In case of direct interpolation, we have constructed a cube comprising of 8 vertices. Now, P is the point where the intensity is required, and perpendiculars P1 and P2 are dropped on the upper and lower faces of the cube. From P1 and P2, perpendiculars Q1, Q2, Q3, and Q4 are dropped on the respective edges of the cube. Now Q1, Q2, Q3 and Q4 will be interpolated in the y direction using the index volume as computed in the previous section for the y-axis for that interval. Now using the interpolated values of Q1 and Q2, P1 can be interpolated in the z direction, and using Q3 and Q4, P2 can be interpolated in the z direction. Now using the values of P1 and P2 thus obtained, the value of P can be interpolated in the x direction with the index volume for that interval. Next, we will show that B-spline interpolation will produce better results. In this case, we have upsampled using B-spline interpolation. Here upsampling is done by a factor of 2, which results in a volume upsampling of 8. As we can see, interpolation is done first for the x-axis, then for the z-axis, then for the y-axis, in this order. Now based on the type of variation, the between the sample points xi, yz and xi plus 1 yz, interpolation will be given for x-axis as follows. If it's a no change or constant region, then the interpolation will be given by a function, this e of x, I, y, z. If it's a linearly varying region, then the interpolation will be given by this function. If it is a cubically varying region, then the interpolation will be given by this function. Now, if the original dimensions before this interpolation was a, b, c, then following the x-axis interpolation, the dimensions become 2a minus 1, b, c. Similarly, this can be done along the z-axis, after which the interpolation results will produce a dimension change of 2a minus 1, b and 2c minus 1. Following this, the y-axis interpolation will be done, and finally the dimensions will become 2a minus 1, 2b minus 1, 2c minus 1. As we can see, this is an image after upsampling using the B-spline interpolation by a factor of 2. Now, in order to implement raycasting on MATLAB, we have made use of the concept of viewing plane. Now we have assigned a particular viewing direction, say M, and the viewing plane is parallel to M. Now we have taken two orthonormal vectors on this plane, and these are computed, and the other grid points on the viewing plane can then be easily found from the integral multiples of these grid points. The intermediate, now let us consider the position vector of a grid point as n. Then the equation of the line passing through the plane, and that point becomes n plus mt. To solve this equation, we take all the planes along the 6 edges of a cube, and this will give us the endpoints of the line. The intermediate points between the extremities along the line are separated by the fixed sampling distance, and these are computed. The intensity values of these intermediate points are then summed up to yield the weighted intensity level at point n. The set of all such points and their corresponding weighted intensity levels gives the volume rendered image. As we can see, this is the result. Here the viewing vector is 1, 1, 1. Here the viewing vector is 1, 0, 0. And here the viewing vector is 1, 0, 1. Now we have made an analysis in terms of the runtime. As we can see, the runtime for adaptive interpolation without upsampling using B-spline is around 787 seconds. Whereas in case of upsampled adaptive interpolation, the runtime is merely 59.3 seconds. This simulation is done for the viewing vector 101, as we have seen here. Finally, we will try to delve into the advantages of B-splines. One of the earliest works on volume rendering was actually done by Taita in 1984, in which the nearest neighbor method was proposed for volume rendering. This method is currently used as the direct interpolation method. Bilinear interpolation is also conventionally used on account of its simplicity and its lower runtime. However, bilinear interpolation is found to be riddled with staircase effects, and the image quality suffers from blurring due to continuity constraints throughout the image. Using wavelet transform, the edges are preserved. Discrete wavelet transforms allows wavelets to be sampled discretely, and they are highly successful in accurate approximation in non-edge areas. Also, B-spline reproduces all polynomials perfectly up to degree m, and it renders an exceedingly high quality of image compared to linear interpolation. Also, as we have seen, B-spline interpolation requires a much lesser runtime compared to the other conventional methods. Finally, we will conclude by saying that this project has been a qualitative analysis of the use of B-splines in volume rendering. Because it has been simulated on MATLAB, therefore it does not give us a very quantitative understanding of the use of B-splines in ray tracing and volume rendering. However, it does show us that the runtime using B-splines is considerably reduced compared to the conventional methods. Therefore, it is highly successful. Thank you.